Hello everyone. Today we shall be covering our fourth lesson of fluid mechanics, conservation of mass, and the continuity equation. So for this lesson, let's imagine some system here where the red outlines our control volume. Well, for our control volume, if we're operating at the conservation of mass, means all mass in equals all mass out. That means the rate of change of mass with respect to our control volume, or the system mass, is equal to 0, which means I am not building up mass and I'm not reducing mass. It is just constant. Well, the system mass can be expressed with this equation here, where the system mass is equal to the integral of the density with respect to the volume. What this is basically saying is the system mass is equal to the sum of all the density volume element products for the contents of this entire system. Basically, I have this little segment here with some specific volume in it. It has some density, and I have a bunch of those throughout the entire system, just adding them up to get the mass of my system. Well, for the continuity equation, we're dealing with conservation of mass, so the rate of change with respect to time of the mass within our system is equal to 0. So we have to take the derivative of this with respect to time. So dm dt is equal to d dt of the integral of our system of rho dv. And remember, this is with respect to volume in fluid mechanics. Now this equation here, using the Reynolds transport theorem, which I've not covered here because some fluid mechanics classes, actually quite a few of them, do not cover it, and a lot of them you just go to this straight constant equation for this mass. If you want me to create a video for the Reynolds transport theorem, leave a comment and I'll be happy to make that video. So, continuing again, the time rate of change of this integral can be written as partial derivative with respect to time of the integral of the control volume mass of the control volume plus the integral across the control surface of rho times the velocity vector dotted with the normal vector dA. Don't worry, I'm about to explain exactly what this means. So, the mass of the system, based off the previous integral above, is equal to the rate of change of the mass with respect to volume in the control volume itself. That means I am only focusing here on the mass as inside the control volume. How is that density changing with respect to volume? And then how is that changing with respect to time? That is what this statement here states. Now what about this one? Well, I have some surface that the nozzles are coming in and out. M in, M out. So that surface, I'm going to make it bigger so it's easier for you to see. Here we go. Through the normal, I'm going to have some normal vector pointing outwards, always pointing outwards. So the normal vector for this area, by the way, it's for the inlets and outlets of your control surface, basically anywhere where mass is leaving your system. So if this entire thing is open, then your entire surface area of your structure would be your control surface. However, I only have one inlet and one outlet. As a result, I'm just focusing on these two areas. So this system, for example, would be my normal vector. Here would be my normal vector. So I'm going to have some velocity coming out here of the fluid leaving or entering the system, and let's call this dA, and I want to know the speed, the net rate of flow of mass through my control surface. Well, for that I need the dot product because I need to know, okay, how much mass is physically leaving this surface as is, because the vertical component, I'm just moving upwards, I'm hitting the wall, I'm not actually leaving the surface. So as a result, I do the dot product and I integrate this entire system, sum up all these elements across the entire area in which mass is leaving my control volume. Again, there's just one inlet, one outlet for this, so I'm just looking at this circular diameter here and this circular diameter here. If this entire thing was open, I'd be looking at the entire surface area of my control volume. So let's move on. Let's go down here, write it again. So dt of the integral of the system, rho dv, is equal to partial, sorry, that's a partial derivative, partial t, integral control volume, rho dv dv, plus the integral control surface rho v dot n dA. Again, this v with the line through it is the volume. This v with no line through it is the velocity of the flow. So, well, remember, we're operating here under the assumption of conservation of mass. The rate change of mass with respect to time is 0. As a result, this entire equation is equal to 0, and there is no change of the mass with respect to time. Therefore, this integral is equal to 0. So, for the continuity equation, a lot of the time it's being derived down into Cs rho of v dot n dA. And then we're going to go over some simplifications of this, and the meaning behind this, and then we're going to do an example. Well, since I'm dealing with the velocity of the flowing through it, and there's no changes to the mass structure inside the control volume itself, everything that's happening to it is when the mass enters and when the mass leaves. As a result, this equation ends up becoming the sum, or can be simplified to the sum of the mass flow rate leaving minus the sum of the mass that is flowing in, which again would be equal to 0 because there's no buildup. It's what it comes in has to come out. So that's why I said earlier we were focusing on this inlet and this exit. And you might have noticed before when we would do I think VD squared, or here we go. I remember now, where we'd say the flow rate of the system's constant. And so if we had, for our Bernoulli's equations, we had like a big orifice like this. So we did v d squared pi over 4. We'll say this is d, and we'll say this is little d, is equal to v little d squared pi over 4. Well, this is the velocity going normal to the surface is equal to the area of the surface. I mean, if we want to know the mass flow rate, we would simply multiply it by the density, and that would get us the mass flow rate of our system going in, going out. So this equation here is just the integration aspect for if you don't have if you have a velocity that changes with respect to certain elements of your area, or you have a density that changes with respect to your surface. If everything is constant or you're dealing with averages, you could just go straight up to this equation, which we used earlier in our previous videos. So now let's do an example where we don't have a so nice system where we can just disregard everything. Well, let's have this here, and then let me draw this pipe that goes up like this, and then I'll draw a bottom part here, and then it goes like here. So I have some flow coming in here, with the velocity v0, which means it just entered the stream. As a result, it has a uniform velocity across. The shear and no slip conditions have not yet taken effect. Well, farther down the line, because this will be a fully developed flow, so we're going to say when it's fully developed, we're going to have a flow here that looks how a flow would look inside of a pipe. It's going to look like a parabola here. And we'll say this profile has a velocity profile 4y minus 2y squared, and we'll say this has a height of 0.75 meters. This is a height of 1 meter. We're going to say it's a rectangular cross-sectional area where this is h and this is w, where this direction, x, y, this direction here is h. So we want to know what v0 is equal to. Let's find that out. Well, we're going to say follow under the assumptions of steady state and that this flow is fully developed. Well, that's steady state, it is fully developed. So you don't have to say this first part. A lot of the time they're indistinguishable. You can have a fully developed flow that's constantly changing, but you're only going to cover that when you get to turbulent flow, which will be in your second quarter or semester of fluid mechanics, depending on what type of course you're doing. For this scenario, we're going to assume steady state and fully developed flow are the same thing. They will not be the same thing later on. At least they weren't with my class. They might have been with yours. Depends how the professors define. So let's continue. So remember, since I write out my equation first, integral of my system, rho dv is equal to partial derivative of time with respect to time of the control volume, rho dv is equal, plus integral of the control surface, rho v bar dot n dA. Alright, again, steady state will equal 0. And since steady state, this also goes to 0 because with respect to time, derivative with respect to time is, again, 0. So what we're left over is this equation here, which again is the sum of the masses flowing in and the sum of the masses flowing out, equals 0. Well, let's plug this in because we have two control surfaces where mass is leaving. We have to focus on those two control surfaces. So let's sum them up. So we'll do the inlet first. So if I do my normal vector, remember it's pointing outwards from the control area. So that's my normal vector. My velocity vector, which is pointing into the flow, is pointing the opposite direction of my end bar, but they are parallel. So it's 180 degrees. Therefore, this is going to be the negative integral of 0 to 0.75 v naught w dy. Again, I have this as w in the y direction going to height h. That's the y direction. And it's negative because the velocity vector is 180 degrees away from the normal vector. Alright, so plus, because again it's integral, we're summing everything up. So this velocity profile is parallel to the normal vector and is pointing in the same direction. Therefore, it's going to be a positive dot product. That's the magnitude of the velocity profile. So that is equal to plus 0 to 1, because it's 0 to 1 as my height, times rho, forgot density here, density times 4y minus 2y squared dy, forgot w again. There we go. W dy is equal to 0. So w is constant, rho is constant. Let's pull that out. So I get rho w times the negative integral from 0 to 0.75 v naught dy plus integral from 0 to 1 4y minus 2y squared dy equal to 0. W and rho cancel out because just dividing both sides by them, 0 divided by anything is 0. Anything except 0. That gets more complicated, but you took calculus at this point, so you should know how to handle that. If you don't, I'll have a series of calculus coming up shortly. So we're left over with the negative integral from 0 to 0.75 v naught dy plus the integral from 0 to 1 4y minus 2y squared dy equals 0. Subtract v naught dy to the other side, so dy is equal to integral from 0 to 1 4y minus 2y squared dy, and then just solve the integral. V naught y from 0 to 0.75 is equal to 2y squared minus 2/3 y cubed from 0 to 1, and you get 0.75 v naught is equal to 2 minus 2/3, so v naught is equal to 16/9 meters per second. There you go. So by using the continuity equation here, we are able to analyze the flow as operating in steady state, and with conservation of mass, everything comes in, everything comes out. That's why you do fully developed and steady state, because if it's not fully developed or steady state, that means the mass going in is building up. This equation up here will not equal 0, it'll equal some number, but if it equals some number, some function, your math just gets more complicated, but your physics doesn't change. Your physics does change, but I mean your process doesn't change by that. So instead of 0, you just have some function, some number, it doesn't really matter. So, like I said, solve the integral here, and as you keep going, this is just math at this point. This was the last part of calculus right here, or not calculus, the last part of fluid mechanics right here. Everything after that, just calculus and solving the integral, and you're going to end with the initial velocity being 16/9 meters per second. Thank you all for joining me. My next video will be on applying this to Newton's second law, which is F equals ma, or F equals ma, or F is equal to the change of momentum with respect to time. And I'll see you all then. Have a good night.